for this opportunity for this talk. Once again, and we hope we'll be doing this over and over over the future years.
Yeah.
So whatever ma'am said, it's a lot about me. I don't think I deserve that much of credit. Anyway, so today's topic that we'll be discussing is knowledge graphs in NLP. First of all, please do let me know if you can see my screen and if I'm audible to you.
Very well.
Okay, great. Okay, so what I'll do is during the presentation, I'll keep my video off, okay, because of some network issues at my end recently. So once we go into question answering and or when we discuss, I'll switch the video on. Is that fine, Sarika ma'am?
Yeah, for me it is perfectly fine, and I hope for audience also.
Okay, great. Thanks a lot. Okay, so what we'll be talking about today is so knowledge graphs are used in so many of the domains across AI and even across domains. So the main objective of using knowledge graphs is to remove the domain barrier, right? So only machine learning or AI experts are able to use knowledge graphs. That should not be the case, right? The underlying semantic content of any type of data should be understandable for any layman. Okay, so that is the major point for which semantic intelligence, semantic technologies, and knowledge graphs, ontologies, all these are used. Okay, and they are slowly starting to gain a lot of momentum recently with things like knowledge graph embeddings, which are coming in, especially in the NLP domain. Also in explainable AI, in artificial general intelligence, knowledge graphs have started being used of late over the last 2-3 years. So what we'll be discussing today is given the problem of NLP applications like search or say question answering, chatbots, how do we leverage the tool or the brilliance of knowledge graphs, and how do we use them for NLP applications? That is the and how, and once we build that, how do we build that first of all, and once we build that, how can we use that for different natural language processing applications? So that is the main focus point, and I've tried to keep it as simple as possible. We'll be also going through some code where we'll be I'll be showing you how we can take some unstructured data and then we can build knowledge graphs from that. Okay. So the agenda, as I discussed, is first of all knowledge graph representation in natural language processing, and as part of that, what we'll do is we'll try to understand how do we extract information from unstructured data that we can use for building or constructing knowledge graphs. Okay, so when the data is unstructured, we can't do anything with it. So a recent report by IDC says that around 80% of the textual data that is available online is 80% of the data that is available online is textual in nature. Okay, so this is like a huge bank of data, but it is unstructured in nature. So what do we do with that? So we have to find ways of tapping into that data and using that data, right? So first we learn how to extract information, useful information, relevant information from unstructured text. Then we understand how to construct a knowledge graph from this relevant information that we have extracted. Then we'll look at knowledge graph visualization. So this is just for a visualization purpose. So it does not help you obviously in when you are using knowledge graphs for certain NLP or any sort of applications, but I'll show you through code as well how we can visualize knowledge graphs for NLP specifically. Then we'll look at some applications in NLP that use knowledge graphs, and I'll also tell you how we can leverage the knowledge that is captured in the knowledge graphs to be used in certain NLP applications. I'll be showing you one use case of that. And we'll also do one demonstration of given unstructured text. How do we construct a knowledge graph from that? Okay. So first we'll talk about how do we construct knowledge graphs from unstructured textual data. So as I said, like terabytes and terabytes of data are available online, right? 80% of the online data is textual in form. So how do we leverage that data? How do we capture that data and make some meaning out of it, extract information from that, and then build a knowledge graph that can be used for further for different sort of NLP applications. So first, let us see how a knowledge graph is represented when I convert some unstructured text into a knowledge graph. Okay, let us just have a look at how it's represented. Why are we using knowledge graphs? I've told this in different ways, but one way of looking at it is able to capture higher order interdependencies in unstructured textual data. Okay. That is a very key point when we are building NLP applications. If we find interdependencies between different textual tokens like sentences, paragraphs, words, whatever the case may be. So it helps us in finding useful information from some sort of unstructured textual data, right? So knowledge graphs is a primary instrument for doing that. Let us take an example of 3 sentences. So I'm a big Lionel Messi fan, so I've put his name here just as a tribute. So we have 3 sentences, for example. Lionel Messi plays for Football Club Barcelona. Lionel Messi represents Argentina. And Buenos Aires is in Argentina. Okay, so these are 3 sentences. So this is not exactly unstructured data in the textual data in the pure form. What I can say is this is some sort of pre-processing has gone into it and removing certain sort of unnecessary information that has gone into it. I'll be showing all of that when we come to it. So, for example, these are 3 sentences which are there. This is unstructured. There is nothing, no information about this data. Right? So, how can we represent this unstructured data through a knowledge graph? Okay. The first thing that we need to understand is knowledge graphs are consisted of nodes and edges. Right. So, the first node that we obviously will be constructing here is a node with Lionel Messi. For the first sentence, what we do is we build an edge which says plays for, and plays for whom? Plays for FC Barcelona. So this is a node edge node representation of the first sentence. Similarly, for the second sentence, we can say it's the same node because it's Lionel Messi. We have already created a node for that. There is no point in redundancy, right? So Lionel Messi represents Argentina. And finally, the third sentence is Buenos Aires is in Argentina. So this is how an unstructured textual data would be represented using a knowledge graph. Okay. So this is what our aim is. Okay. What we'll be trying to do. Given unstructured textual data, how do we convert that into a knowledge graph representation? Okay. But the key point that we have to keep in mind is we have to do this automatically using some language-based techniques or some AI techniques without manual efforts. With manual efforts, it will take so much of time given terabytes of data. It will take years and years to build a knowledge graph representation. So how can we do this automatically using certain NLP tools, using certain linguistic knowledge, using certain knowledge in artificial intelligence? How can we build this automatically without any sort of manual efforts? Okay. So I'll give you an overview of how exactly this process is done, starting from the unstructured data, which is a set of documents which can be tweets, which can be blogs, which can be Wikipedia content, which can be books, like online version of books, right? So this is unstructured text, right? And this is huge in content. Okay, so this is the starting point for us. So what do we do next? First, we do something called pre-process or cleaning of the text. Okay, so we there are certain NLP processes for um, cleaning of text and pre-processing. I'll not go into details of that. I'll show you an example which will sort of make it clear. Our main focus is how do we build the knowledge graph. That part we'll be concentrating. So this is an NLP specific thing. So how do we'll pre-process or clean the text. So what do we do in this? For example, we remove punctuations. We remove something called stop words. Stop words are words like the all these things. Okay, so it's an optional thing. So there are different tools available for pre-processing. You can use some of them, like there is something called stemming, lemmatization, where you are finding the root words. For example, the word going will become go, right? So there are different ways of pre-processing and cleaning text. You can choose which option to take. First, we take the raw text, the set of documents that we have, the unstructured text that we have, we pre-process and clean the text first. Okay. Then what we do is we do something called text segmentation. So we have already cleaned the text. Now what we do is we divide that text, segment that text into language tokens. Okay, that may be sentences, that may be paragraphs. In this case, in our implementation today, we'll consider the text unit as a sentence. Okay, it can be word level, it can be phrase level, whatever it is. So we'll have to segment that text so that that part of the information. So if it's a sentence, whatever information is captured in each sentence will be represented as a node, edge node in a knowledge graph. Okay, two nodes connected by an edge. That is what, or like those nodes can be common, but a new edge might be created. Okay, given the information is not redundant. So that is what we'll do. So we'll segment the text in such a way so that every unit of that text would be a new information in that knowledge graph. Okay. But once we have segmented the text, we have to extract that information, right? The useful information. That is done using something called information extraction. We'll spend a lot of time around information extraction because that is the focal point, that is the pivotal point of this entire process. Information extraction. So pre-processing and cleaning of text is a very trivial procedure. Text segmentation is also not a very complicated process. The complicated process is information extraction. How do we take that unit of text that has to be converted into a knowledge graph to extract the required information and then translate that into a knowledge graph representation? So that is what the overview of building a knowledge graph from unstructured text looks like. We start with unstructured text, clean it, segment it, extract its useful information, and build a knowledge graph representation. Okay. So in case you have any questions, drop it in the chat whenever I can. I'll keep replying to it. Okay. I want to make this session more interactive because we have code as well. Okay. So first step, as I said, is pre-processing and text segmentation. So I hope I have kept most of the examples from the perspective of Indians, right? Because ma'am informed me all the participants are from our country. So I've taken the example of a very famous Indian singer, Kishore Kumar. I think many of you will be fans of Kishore Kumar, right? So this is extracted from Wikipedia directly. So Wikipedia is obviously unstructured text. It does not have any labeling to it. It does not have any information marking to it, right? So this is the unstructured text that we have. So what is the first step? As we said, pre-processing. Like we have to clean the text. So when we clean the text, this is what we get. Okay. I'm not reading it out because you can see it on the slide. So given the unstructured text, this is what happens after we pre-process or clean the text. If you notice, I've not removed all the punctuations from here. I've removed some information from here which can be cleaned out, okay, which is not required. So pre-processing is a particular phase in building an NLP modules or NLP applications, which is problem specific. Okay, so in this case, we are building knowledge graph. So we need some information. We don't need some information. So based on that, we'll be building the pre-processing or cleaning module accordingly. Next, we do text segmentation, right? So when we, as I said, in our case, even in the code that I'll be showing, our textual unit would be a sentence. So when we divide this into sentences, so this is basically a sentence segmentation, right? So each of the sentences would be separated. So each of these sentences now will add some information to the knowledge graph, which add one edge to the knowledge graph, one or multiple edges to the knowledge graph, depending on how we are extracting the information. Okay. Any questions at this point, you can please drop in the chat.
Good afternoon, sir.
Yeah, good
Hello.
afternoon. Yeah.
This is Optimal. Sir, actually, you have just you have kept the first sentence, but you have just ignored the content inside that bracket. Is it intentional or something for easy to understand?
I didn't get you, sorry. Which part are you talking about?
So in the first sentence,
Okay.
so within the bracket actually, born Abhas Kumar Ganguly, the first sentence.
Right. No, I've cleaned that out just for brevity, just for make it easier to understand. So in order to do this,
Okay, thank you, sir.
I can make it as complicated as possible. So this is
Okay.
for,
Okay, sir. Thank you.
okay. Yeah, thanks. Okay, so the next part is the information extraction. So first we have got some unstructured text, we have pre-processed it, we have cleaned it, and then now we have already segmented that text. Now comes the most important part of building the knowledge graphs from text, which is how to extract relevant information from the unstructured textual data, which is called information extraction. So let us go back to the first knowledge graph that we saw, the representation that we saw. A subset of that, I've left out the Buenos Aires part here. So here we can see there are 3 nodes and there are 2 connecting edges, right? From Lionel Messi to FC Barcelona, we have plays for, and Lionel Messi to Argentina, we have represents. Okay. So first, let us look at the nodes, just the nodes. There are 3 nodes. Lionel Messi is on one side, and it's obviously knowledge graph is a directed graph, right? So that is why we have edges that are directed to FC Barcelona and Argentina. In case of NLP or information extraction, this is called the head entity, where the edge starts from, and where the edge ends, it's called candidate entities. Okay, so FC Barcelona and Argentina are each candidate entity, and Lionel Messi is the head entity. Okay, so the process of extracting these entities is called entity extraction. Okay. Now we are left with the edges, plays for and represents. These are called relations, as most of you would be knowing. And the process of extracting relation is called relation extraction. So what is information extraction? Combining entity extraction and relation extraction, we get information extraction. So when we extract the entities and relations, we are good to go for building the knowledge graph, right? So we have the nodes which are represented by the entities, and we have the edges which are represented, we have the relations which are represented by the edges. Okay, so now that we have the set of nodes and we have the set of edges, and we know what to connect with whom, we can build the knowledge graph in that case. So what is the main part of information extraction? First, entity extraction, where we are extracting the nodes, the source and the target nodes, which is the head entity and the candidate entity. And then we are extracting the edges, which is the relation extraction. So now our information extraction problem is divided into 2 problems. One is entity extraction and the other is relation extraction. So some small points about entity and relation extraction from text. Entity extraction is a subset of a larger class of NLP problems called NER, or named entity recognition. I'll be showing you a demo of that. So what happens with NER is, in most of the cases, I'll actually switch to this. It will be easier for you to understand. So this is a tool called Displacy, which is a sort of visualization tool for a very famous NLP tool called Spacey. So if I say, so Apurva,
Could you kindly drop the link also in the chat box if you want the participants in parallel to explore?
I'll be sharing the slides. If that is
Okay.
fine, the link is there in the slide itself. Is that
Okay, right. In parallel, you do not require that way. Then it is fine.
Yeah.
Okay.
So suppose Apurva just spoke to me, right? I guess Apurva was his name. So let's say Apurva spoke to me. So it's not able to find anything. Now if I change this, Apurva spoke to me. Or maybe we can give a very famous name, say okay, this would be great, but anyway, let us put it. So it has identified Narendra Modi as a person. So these on the right, if you see, these are the entity labels, which means it identifies person, um, organizations. Okay, GP is a geopolitical entity. For example, if I say Narendra Modi is the Prime Minister of India. So it has identified India as a GPE, but it is not. So Prime Minister is basically not an entity in this case. We can. I don't think there are entities to classify Prime Minister as a position. Okay, so we can search for something else. For example, say. Name and I forgot the third person's name, so let us put it this way. Okay, so it has identified Apple Incorporated as an organization, Steve Jobs and Steve Wozniak as persons. But as soon as I put, say for example, my name, say, so it is not identified any entities. So you see, this is a name, right? But it has not identified it as a person. When I gave Narendra Modi, it has identified. So the thing is, this is one of the best named entity recognizers which are there. Okay, it is built on.
Hello.
Yeah.
Please tell me from where are these entity labels coming?
Okay, so this is from an NLP tool called Spacey. Okay, and this is the named entity visualizer of Spacey, which is called Displacey. Okay, I have so this link which is there, you can directly go to it from the slide itself.
That is fine. That is fine. The entity labels on the right hand side, are they fixed for this visualizer?
So these are the set, so you can choose or click or unclick any.
Okay, cannot we input our own vocabulary model?
Yes, it can be done. It can be done. That can be done. So
They allow.
your own model with the supervised data set. You have to have the entity annotated data, and you can add to whatever data is existing for species. So
see the data I am putting here only as you are writing the data, it is fine. But entity labels, maybe I do not want these entity labels which are being displayed here.
For domain specific purposes, I want certain types of entities.
Yes.
Yeah, that can be done.
So they want me, they allow me to upload that.
So they will give you an API and interface for training your own data. You can use their algorithm, you can use their platform, their APIs to train your own data.
Okay, right.
Okay, so I was saying just as I said, NER is built using several machine learning and deep learning techniques, and there are several drawbacks of classical NER to build knowledge graph specifically. So as you saw in the example, like names like Apurva or Arindam, so these names they'll not identify because it is probably not in the data set. Okay, so we have to think of more classical techniques in NLP for solving this problem. That is what we'll be exploring today. Okay. So what is the solution to that? We look at the grammar and structure of sentences. We go at the base of language and try to identify grammar and structure to extract the entities and relations. For this, we'll be using a classical NLP tool called Dependency Parsing. We'll be going into that, and I'll also be establishing where exactly we'll be using Dependency Parser in a bit. I will go a bit in depth into entity and relationship extraction. So what we understood from here is if we use the NER model, then our problem is not solved. We'll not be able to extract the information that we need in order to build the knowledge graphs. Okay. So let us look at how a different angle of entity extraction here. Not like entities like person or like organization or geopolitical entities. Okay, let us look at entity extraction from a very different angle, from a much more simpler angle, as like Einstein has also said, right? The best solution to a problem is the simplest one. So let us look at the simplest solution to this problem. Let us go to the basics of language that we have all learned when we were in school, and let us use that, because we have to solve a problem based on the end goal. We are trying to build a knowledge graph. We have to think of that. In order to build a knowledge graph, we have to find the nodes and we have to find the edges. So what do we need to extract from the unstructured text to achieve that, right? So we'll look at entity extraction from a different angle. Say, for example, we have this sentence, Vishwanathan Anand plays chess. Obviously, this would have been recognized by the NER, but I'm just showing a different angle of looking at it. So these are my two entities, the head entity and the candidate entity, right? We already know this. We have to extract these two entities from here. But if I say there is another way of looking at this, if I say the head entity is the subject of this sentence and the candidate entity is the object of the sentence, I'm sure you would remember in the initial years of school, we have learned about structure and grammar, the famous book called Wren and Martin, right? So we learned about subject and object there. In a sentence, we'll have a subject which is the main focal point in a sentence, and the object on which the action is happening, right? So Vishwanathan Anand is the subject, the head entity, the head node, the starting node, the source node. And what is the target node? It's the object. Okay. So for a different example, if I say Sholay was a great movie, what will be my head entity and candidate entity? Or to put it in a different way, the subject and the object. Sholay obviously is the subject and movie will be the object. Here I have not included great movie because great is called a modifier of the object, which means it's sort of giving some extra meaning to that. If I say Sholay was a movie, that's absolutely fine. That is a full form sentence. If I say Sholay was a great movie, great here is also called a modifier, okay, which is sort of adding more information to the object. So we'll be capturing all these things also in some cases, okay. But this is a different angle of looking at entity extraction, where instead of thinking of extracting entities and using high powered deep learning or machine learning methods to extract these, I know those will be able to do this, but like let us look at this from a very simple angle. And obviously if I am going to train a deep learning model for a 2-hour session, that's not possible anyway. But what I'm trying to see is we can look at a simpler solution for this problem, and this is one of the ways that knowledge graphs are built for NLP applications. Okay, So again, relation extraction from unstructured text. So now we know that in order to extract the entities, what we have to do is we have to go into the structure, the grammar of the sentence, and then we'll have to find the subject and the object. Let us take the same example for relation extraction. What is the relation here? Place. This is the edge in our knowledge graph. If we go back to our Renan Martin, what does Renan Martin say? What is place here? It's predicate, right? Again, for the same example that we took in the previous slide, Sholay was a great movie. What is the predicate here? It is was, right? So if we extract the subject, object, and predicate from sentences, we have our source node, target node, and edge, right? Then we can build the knowledge graph. So to summarize what we just learned, in order to build the knowledge graph representation, the focal point is information extraction. Okay. So for information extraction, instead of trying to find out what are the entities, then what are the relation between these entities and making it more complex, the simplest way to do this is finding the subject of the sentence. I'm talking strictly about when we are doing sentence level segmentation. Finding the object and then finding the relation between these two, which is the predicate. So we find the subject, predicate, and object. So we've come till here. First, we have taken unstructured text. We have cleaned that. We have segmented that into sentences. From sentences, now we know we have to find the subject, predicate, and object. We have come till here, and we know that if we do this, possibly we'll be able to build a knowledge graph from unstructured text. Okay. But how do we find the subject, predicate, and object? We can't do it manually. We don't have Renan Martin sitting at one end and taking each sentence and telling me, okay, this is the subject, this is the object, this is the predicate. So what NLP tools do we have in order to do this? How do we do this? We do this using an NLP tool that I had mentioned earlier, which is called a dependency parser. A dependency parser will help us find the subject, predicate, object, and a lot more information from this unstructured text. Okay. That will conclude our information extraction part for knowledge graph building. So let us look at dependency parsing. If you have any questions at this point, please go ahead and ask. Okay, I think I made it too simple, is it?
Sir, in case of multi-word predicate, if I have a predicate like this, because you have shown an example, plays for,
right?
Messi plays for. So,
right.
So plays for this kind of predicate. So then only actually you have shown was is basically
yes.
a word.
Example, I have to show a simpler one, right? Yeah, I'm getting your point. So we through dependency parser, we will be able to extract all. You're talking about multi-word predicates, we'll be able to extract all. So
Thank
we'll
you,
be seeing, so we'll be taking unstructured text from there. We'll be seeing predicates like written by, composed by, directed by, all these predicates which will come into that. And that's a good question actually. So we will definitely be extracting multi-word entities, multi-word predicates also, like multi-word relations also. Okay, does that answer your question?
Yes. Yes.
Okay, so let's look at dependency.
Otherwise, also Vishnathan Anand has already been taken as a multi-word subject.
Yeah, correct. Yeah. Yes. So let us look at dependency parsing and how powerful it is and how it can help us in solving our information extraction problem, right? Extracting the subject, object, and predicate. Okay. So to define dependency parsing, just for keeping the definition in the slide, I've put this. It is a process of analyzing the grammatical structure of a sentence, and it captures the dependencies between words in a sentence. Okay, we'll see exactly how it is done. I'll show you a demo also of a dependency parser. Again, using the same NLP tool, which is one of my favorites these days. It's called Spacey, because like Spacey and Hugging Face, these are two tools where they have included a lot of transformer-based architectures, and it has a lot of leverage around it. It has a lot of features, and it has pre-trained models and APIs. If you are like in NLP or wanting to move into NLP, I think these are great tools that you can use for research as well as productization as well. Okay, these are open source. Okay, so dependency parser. So for example, if we have a sentence, John can hit the ball. Okay, so if we see the dependency parser output of this, it is like this. So first thing that goes into that happens in a dependency parser is the sentence is labeled using part of speech tags, which you can see in the third line. So NNP means a proper noun. Okay, VB means a verb, determinant, NN is a noun. Okay, so the root is the focal point of the sentence. So who hit the ball? John hit the ball. What did John hit? The ball. Okay, this is the object and this is the subject. So we have our object and subject here. Now how we find the predicate, that can also happen using a dependency parser. Okay, so you can understand, right away it is identifying the subject and the object. Okay. So 66.66% of my problem is solved. Only 33% of the problem remains. Right, finding the predicate. So that can be found around the root. Okay, we'll see exactly how we can do that. Okay, first let us look at a demonstration of the Spacey dependency. So for example, the sentence, same sentence, like is for Argentina, let us, or we can put multi-word here also. FC. Okay. Okay. So now you can see this is the root. Okay, and this is the adjective for that. Right. So the root directly depends on this. This depends on this. So this entire relation will be captured. So plays for will become my predicate. So FC Barcelona will become the subject, and Lionel Messi will become the subject, and FC Barcelona will become the object. Okay. So it has captured these tokens directly. So because if I don't give merge phrases, it will possibly not take that, but that is an option that we can. So since I've merged the phrases, it has taken multi-word subject, multi-word object, and then we can combine what is dependent. So plays, so Lionel Messi plays, right? And FC Barcelona depends on for. So the object depends on this, subject depends on this. Combine these two, we get the predicate. Okay. I hope that sort of answers whatever doubts you might have. We can look at more examples. Okay, so let us go to Kishore Kumar again. Kishore Kumar was one of the greatest singers in India. Okay. This is a longer sentence, so obviously the dependency parts will be longer. So Kishore Kumar again is my subject. India is the object. The greatest singers, it has captured here. So it's capturing multi-word expressions as well. So multi-words, it's combining together. Okay. So what would be the graph from this? Kishore Kumar was greatest singers India. Okay, that much information is good enough. Fine. So for the knowledge. So what I'm trying to say is, if we look at an alternative approach for entity extraction and relation extraction, if we think of extracting the subject, object, and predicate, not from strictly from a language perspective, from an NLP perspective, we can combine these into bigger blocks, like not only single words. So I don't take only Kumar here, I take Kishore Kumar here, right? In the previous example, I will not just take place, I'll take place for. So that is how we can play around with it, right? Not exactly what we are trying to do here. The predicate would have been place. I'm taking place for here as my relation, right? So that can be achieved using dependency parser. And once we get the dependency labels, these are called the dependency labels: subject, attribute, preposition, okay, object. So that's what, like, we can extract based on the dependency labels. We can combine different dependency labels, words with different dependency labels, to get our nodes and edges. Okay, we'll be seeing all of this operational when we go into the code. Any questions at this point? So for people who are interested, they can use this particular paper. This is one of the seminal papers in dependency parsing. So if you want to build an universal dependency parser from scratch, and it's a paper by Christopher Manning, who is sort of one of the fathers of natural language processing. Okay. So Christopher Manning, the book that we start in NLP with is Christopher Manning's book. So it's a paper by Stanford University. They have their own dependency parser also, but Spacey is open source. It's right now it's a bit better than Stanford dependency parser. Okay, so if you want to build from scratch, hi Nidhi, it's there in the slide. Nidhi asks, please share the link to the paper. I've put all the links in the slides itself so that you don't have to go anywhere else. So if you want to build from scratch, you can go to this paper. Okay, you can go through this paper, and you can find a GitHub link also. If you go to Papers with Code website, you will get the GitHub link for this also. So you can have your own data and build your dependency. Okay, so now that we are done with dependency parser, so now we have, what we have seen is, we have taken unstructured text, we have cleaned it, we have segmented the text, we have extracted useful information from it that will create the nodes and the edges for our knowledge graph. Now let us see a small visualization of how a knowledge graph looks like, when a big knowledge graph looks like when we build it for unstructured text in NLP. How does it look like? So this is a sort of representation of a knowledge graph, how it looks like. So I have said an entity called document here. I have an entity called location here. A document can mention a person, it can mention about money, it can mention about a keyword, a location, it can mention about a title and an organization. Okay, so this is called mentions and the particular entity. A person has title, right? Then between two entities, so an organization received money. So you see how a knowledge graph in NLP would look like if it's extracted from a certain textual, unstructured text, textual, segmented textual data. It would sort of look like this. We'll look at a lot more of knowledge graphs when we go into the code. We'll take unstructured data from Wikipedia and build a knowledge graph from that. So to summarize what we have learned so far, after I go into the summary, you can, I'll take 5 minutes out. You can go ahead and ask questions. Okay. Abhishek, I'll get to your question. Let me finish off with this line. Okay. So the first step is data extraction. Okay. I've not mentioned data extraction part because it's not related to knowledge graphs at all. It's more related to NLP. But obviously, like, if you have to build a knowledge graph for natural language processing, you need to follow the data extraction procedure of natural language processing, right? So we can extract required unstructured data from tweets, blogs, Wikipedia, as I said, or domain-specific documents if you want to build a domain-specific knowledge graph. Okay, so if you want to build a knowledge graph, say for Indian Railways, okay, you extract unstructured data for Indian Railways from railway websites or IRCTC website or wherever it is. Right? So the first step is data extraction. Second step, as we know, pre-process, clean the data, remove punctuation, stop words, text normalization like stemming, lemmatization, where we reduce the inflectional form of words like going into the base form like go. So first data extraction, then pre-processing of that data. We have cleaned the data now. Now what do? We segment the text. In our case, whatever we have seen so far, it is sentence level. It can be smaller or bigger, depending on what sort of knowledge graph you're trying to build. You can segment the text accordingly. Okay, so we have to segment the text into individual textual tokens depending on what sort of knowledge graphs or what sort of problem you're trying to solve. Again, the knowledge graph would be used for some NLP application, right? So it also depends on the application that you're trying to build. Okay, then we have information extraction, the most key part of this entire process. Information extraction, what do? We extract entities and relations, which are basically nodes and edges of the knowledge graph, and we extract the triplet subject, predicate, object. Okay. Next, we go into the knowledge graph construction. So we create the knowledge graph from the information extracted. I'll show how we can do this using Python once we have extracted the knowledge graph, and how we can visualize that as well. So after the useful information is extracted from the unstructured text, we build the knowledge graph and then finally use that knowledge graph for building NLP applications. Okay, so this is the entire procedure which I've shown sort of in a timeline. The process step by step, what needs to be followed for building knowledge graphs for natural language processing. Okay, so you can go ahead and ask questions now.
Sir, how to visualize this graph that we have shown?
I'll come into visualization. So when we go into the code, I can't show it in the slide. I'll show it in the code how we can visualize graphs.
Okay, sir. Thank you.
Once we extract the data, I'll show you how we can visualize it. Okay, ma'am, can we take a break of 5 minutes now?
Yeah, sure. All up to you.
Okay.
Begin.
So you can drop in your questions. Keep dropping your questions, and let us take a break of say 2-3 minutes. You can keep dropping your questions. I'll just have some water and then. Hi guys. So Abhishek Sharma has asked a question: how to represent information that depends on more than one values, properties, predicate. Okay, okay, like Ronaldo. Okay, Ronaldo fan. Great.
I'm not specifically a fan, but Messi didn't play for more than one club.
Okay, it's fine. Played real. Okay, for Manu from. Okay, so the thing is, for such, so as I said, textual segmentation, what we are doing is at a sentence level, right? So what the problem that you're seeing is like the textual segmentation would be at a phrase level, say component level. So we extract Ronaldo played for Manchester from such and such date. First knowledge snippet that we have. Second knowledge snippet is played for Real Madrid from so this date to this date. Played for Juventus from this date to this date, right? And currently he's playing. So in this we can extract dates also. So that data extraction is again a part of entity recognition. If you go to that portal that I showed you for display C, you'll be seeing there is an entity called dates as well. Okay, so what you do is you don't extract the entire sentence. There is a lot of knowledge snippets that we can form. So what I am trying to say is, when we are building a knowledge graph for NLP, what we try to do is we try to capture information that pertains to, say, one set of source target node and one edge between them. Okay, so when we look at this information, there are so many nodes and edges that we can form, right? So in that case, what we'll do is we'll take that knowledge snippet, we'll extract it phrase wise, not maybe sentence wise. Okay? So again, like, these are a bit old fashioned techniques. Nowadays people build something called knowledge graph embeddings, where we take the entire text and represent it as an embedding of entities and relations. I'll come to that in a bit. There are a lot of recent papers around knowledge graph embeddings. So so if you want from the approach that I am showing, from that approach, what you can do, you can use a dependency parser, but for that, first you have to segment that text, maybe using a phrase structure grammar parser. Okay, from there you extract snippets, you extract phrases out. Okay, and then you use all these phrases to form individual parts of the knowledge graph. Okay, does that answer your question?
Yes, sir. Just one addition to it, like if we don't know how the things will go in the future, like Messi from year, I guess he was of age 13. From then he's playing for Barcelona,
Right.
and now he's planning to switch, or he can switch. So these things we don't know from the beginning when we are creating the knowledge graph. Then how to in future, how to embed these kind of information, like if, like in the Ronaldo example, it depends on place for, and the date depends on place for and the club name, because it will create ambiguity. Like if we are using only place for or directly fetching the dates, we don't know which club he was playing from this date to this date. Then how to use, how to.
So what you're talking about is updation of the knowledge graph. Okay. So we have an existing knowledge graph, and based on the new information that comes in, how do we update that? So for updation, there are different techniques. One of the techniques that comes to my mind is called incremental learning, where we don't update a knowledge graph model. We don't update the we don't build the knowledge graph from scratch. We don't build a model from scratch. What we do is whatever existing thing is there, based on that we find the entities that are matching, and if we have new entities, and then, so for example, you are building a dictionary. You have a set of documents. Okay, so now you're trying to find out what words are there, a vocabulary of that document, like what unique words are there in that document. So assuming that you guys know Python basics, right? So sorry. So when we are trying to build a dictionary of vocabulary, unique words, So what we do is we check if that word is already there in the dictionary. If it is there, then what we do is we increase the count, right? So in a similar way, incremental, I'm sort of dumbing it down a lot. The concept of incremental learning, what it basically does is, in case of knowledge graphs, when we're trying to append to a knowledge graph, not sort of build it from scratch, we will see if whatever the new information coming in is, do we have existing nodes that correspond to this information. So when I'm telling Ronaldo played for Manchester United from such and such date, okay, so that is the information that is already there in the knowledge graph, okay. But say at the time he moved to Real Madrid from Manchester United, that information is something that has come in fresh, right? So I'll check if already Real Madrid is, a node called Real Madrid is there in my knowledge graph, a node called Cristiano Ronaldo is there in my knowledge graph. So if it is there, I'll get an edge between those two. It's just adding to the knowledge graph rather than building it again from scratch. So does that answer your question, or you are looking for something entirely different?
Yes, I answered.
Okay.
Thank you, sir.
Okay, so is dependency parsing different from semantic parsing? Dependency parsing is a type of semantic parsing. So there are different types of parsing techniques. One would be phrase structure parsing. The other is dependency parsing. Okay. So there is shallow parsing as well. So these are different types of semantic parsing. Okay, so Ravindra Kumar Pradhan asks, is reconstruction of sentence part of pre-processing? In some cases, incomplete and disordered sentences have also some meaning and we can understand easily. So, okay, so for example, if you are taking tweets, so the entire way of handling tweets is very different. Tweets have different types of pre-processors. Okay, so we are not trying to reconstruct sentences. That is part of something called natural language generation. We are trying to auto-correct things. So we are not trying to do that. When we are handling tweets, we handle it in a different way. We use different types of parser. Different types of parsers are available for tweets. Okay, so using those parsers, using the acronyms, using the lingo that is used in tweets, which is basically, in most cases, it would be colloquial language, right? So in that cases, the way in which tweets are parsed is completely different. So the tweet parsers will be able to extract information from tweets. So that is part of tweet information extraction. Again, same for any sort of social media. Next question, a sentence in multiple subject and object. Yeah, it's the same thing when it has multiple sentence and multiple object. So in this case, it will extract only one subject and one object, but it can happen that way. But so a sentence which has multiple subject and multiple object can be broken down into multiple phrases, because a phrase will contain one subject and one object in most cases. If I'm going for a noun phrase, it will sort of capture that. But now, so what I'm talking about is parsing based on phrases. I'm not talking about extracting phrases. So if I do say phrase structure parsing, so what I'll do is I'll take a noun phrase and a verb phrase and I'll see if there is any modifier in between, like an adjective or adverb. Okay, so we'll combine this information. We'll first parse it based on the structure of the sentence. So each unit that I'll be getting, from there I can extract single object and single subject. Okay. Okay, so let's move on. You can keep typing your questions, or you can sort of ask me in between. That is also fine. Just start with NLP applications that are built using knowledge graphs. I'll switch the video off because of some network issue that I mentioned. Okay, so what sort of NLP applications use knowledge graphs? the first thing that will always use knowledge graph is a chatbot. Not all chatbots use knowledge graphs. Obviously, it depends on what type of chatbot you are building. But in case you're trying to extract information from the query as well, and you have it's an entity-based chatbot. Okay, so suppose you are building a chatbot for an e-commerce company like Amazon or Flipkart. You have to extract entities. In that case, like Amazon publishes so many papers on knowledge graphs. They have their own platform for knowledge graph itself, for building knowledge graphs. Okay, and it's supposed to be the best one right now. So why are they building knowledge graph based extraction for different types of applications, right? That is because in e-commerce there are a lot of entities there, product names especially, their features. Okay, so those entities are there. So e-commerce is one of the best areas where we can see chatbots using knowledge graphs. Okay. Then we have search engines. So search for a search engine, if you keep the entire data, internet is a web, right? It's a graph structured thing. So knowledge graph again is a graph. So if we have the information, if we have the node structured in a knowledge graph, search becomes easy. So if we match the nodes and the relations that is extracted from the search query, then the search becomes much more faster. Question answering, another thing. I'll be showing a sort of use case on chatbot search engine and question answering, how all of this is used, how knowledge graph is used, helps in building these systems. Question answering is like sort of a subset of a chatbot where you don't interact with the user like that. The user asks a question, you give an answer. There is where it ends. Chatbot is where user asks something, you give an answer, again the user asks something. So there's a dialogue. In question answering, dialogue is not there. But again, the same thing, like if the information extracted is stored in knowledge graph format instead of a different sort of data structure, then the search and the turnaround time for such systems increases a lot. Again, the semantic underlying semantic power of knowledge graphs would be a big plus for such systems if they have a knowledge graphs working at the back end. We have automatic spell corrector. Automatic spell corrector basically is based on grammar. So whenever we build a knowledge graph from that, if we understand that it is built from a parser, and then if we can't build a knowledge graph from a particular sentence because it has been it has sort of been written wrongly, incorrectly, then again we can sort of find the I'm not talking about just spell corrector. I'm also talking about say apps like Grammarly on all, which sort of try to see your grammar as well, right? Spell corrector, again, you are using a knowledge graph to store information related to different words. Right? It is a character based knowledge graph in that case. Machine translation. So from one language, I build a knowledge graph. So I have an understanding of grammar from the knowledge graph, and then I transfer that into a knowledge graph of the other language. And from knowledge graph, again, I create the sentence in other language, like from hello to hola, right? From English to Spanish, English to German, French to German, whatever the case may be. So transform the text into knowledge graph first. From knowledge graph is language agnostic data structure, right? So the same thing we do for the grammar that corresponds to the other language. So that is how we can do machine translation using these steps. Context embeddings, right? As I was talking about knowledge graph embeddings. So if I can capture, so if you know of what word representations are, what word embeddings or textual embeddings are, there are sentence embeddings, there are paragraph embeddings, whatever the case may be. So if we can convert text into a knowledge graph and build embeddings from there, it's a much intelligent way, much more intelligent way of representing a piece of text in an embedding space in a low dimensional vector space, right? So it's not just the words which are being represented, it is the relationship between words and what relation is there between those words. All of these things are being represented in that low dimensional embedding space. Okay, that is what context embeddings, how knowledge graphs help in building better context in embeddings. Okay. Natural language generation. So again, natural language generation is a part of chatbots, is a part of question answering system, even search engines. So when we have to reply using some information that we have, be it a chatbot, be it a search engine, question answering system, information extraction system, whatever it is, if you have to reply in natural language. For example, say if I talk about text summarizer, so if I can build a knowledge graph from the entire text and then sort of find the key nodes there and the key relationships there, I can do a text summarizer using knowledge graphs. There are a lot of research work that have used knowledge graphs for text summarizers. So that is another big application of natural language generation, where we are summarizing a bigger context of text into, like if you have used the app called InShorts, it partially uses text summarizer in 60 words or something, 60 or 100 words, it will sort of give you a news snippet. Virtual assistants like Alexa, Siri, when these virtual assistants are built, they are also called intelligent personal assistants. I've put virtual assistants because it is a much more generic term. So for IPAs or intelligent personal assistants, if the entire information is covered, captured, so it depends on how you are sort of modeling your textual information, how you are storing your textual information. You can store your information as a basic NLP model. You can store your information in a dictionary. You can store your information in a knowledge graph. You have to see based on what application you are building, what would be more suitable. So knowledge graphs are sort of from raw unstructured data, it is able to capture a lot of dependencies that are not clearly visible using basic NLP tools. So that is why a lot of people nowadays are starting to use knowledge graphs for language textual data representation. Okay, and all of this goes into the primary and NLP applications that I've just shown. So let us look at one use case now. The use case would consist of a search engine use case, chatbot use case, or a queue system. So I have a query, for example. So what happens in these systems typically is the user comes up with a query and you have to come out with an answer, right? In some cases, you can form the answer around the actual node, okay? Or in search engine, you just give the answer. In queue system, you can directly give the answer. Chatbot also, you can do that. But you can also build some sort of NLP model which takes the actual data and frames the answer in proper English. So that is not something that I'll be talking about here. So what we are talking about is how do we extract the information, actual information that we have to reply to the user. Suppose the query is which country does Lionel Messi play for? Okay. So what are the useful information, relevant information based on which I can actually query the textual data that has been stored in a knowledge graph format to reply to the user? What are the key words or like, I will not say entities directly, what are the features here that we need to capture? First is Lionel Messi, which is the main focal point of this entire text, and country. Okay. So we can do this using a dependency parser. So right, we can use a dependency parser to find out that, okay, so this person is talking about Lionel Messi, and there will be a direct link between Lionel Messi and a country, as we saw in the dependency graph, dependency parser graph, right? There are links between words, dependencies between words are captured. So Lionel Messi and country, that is there. And what relation are we trying to capture between these primary features, right? Which country does he play for? So what we'll be doing is we'll be searching for entities that relate to Lionel Messi and country, and we'll be looking for relations which relate to play for. So when we use knowledge graphs, it's not exactly an exact match that we are looking for. We use embeddings, which means it's a close enough thing. We're searching for something very close to this. For example, if I have this knowledge graph, this is a part of the entire knowledge graph that I have built from the textual data that we have. So this sort of hovers around Lionel Messi, the different attributes of Lionel Messi, and then I've showed some extensions into that. So FCB or Football Club Barcelona is a type of club. Argentina is a country, right? So these connections will be there. But we are looking for primarily for Lionel Messi here. And there are two types of information here that the system can get confused with. But we have also extracted country and place for. So place for we have already got in both the cases. So what is the deciding factor here? The deciding factor is country. So we extract this part of the knowledge graph, and when we traverse this knowledge graph, we get that Lionel Messi plays for Argentina, which is again a country. So we extract the information that Argentina is the correct answer. So here you see how a knowledge graph has helped us in building a system which replies to the user like a search engine, a chatbot, or a question answering system. Okay, so using the knowledge graph, the knowledge that we have captured in the graphs, in the entire knowledge graph that we have, I've traversed that graph. I've sort of parsed the important relevant information from the input query, and then I've found out the correct answer. Okay. Any questions at this point? You go back to this slide.
Sonika says that, can knowledge graphs be used to answer Boolean queries?
Boolean queries. I don't like what sort of Boolean queries are you talking?
Sonika, do you mean yes or no?
Yes or no?
Yes,
Thing.
With yes or no answers.
Okay.
yes. Either true or false or yes or no.
Yeah, I think it can be. So you have to design the system in that way. So if it's just for a yes and no, you can build a decision tree on top of the knowledge graph, which uses the knowledge graph information.
Yes, you are right. We can fetch that which country this person play for, and we could match it with the input Argentina.
Exactly. Any other questions? Okay, so we don't have a lot of slides to go. I'll quickly complete with whatever I had. I've put some extra information for you guys. So these are some of the recent papers on knowledge graphs. So all of these are links. So whenever you click on one of them, for example, say for new info, if you click this, it will directly open the paper. Okay. And these are all ACL papers. I've kept the best quality papers on this. So these are some of the best quality papers around knowledge graphs and their uses in NLP. So for example, this is on question answering. This is on again checking facts in certain queries. Okay, it's checking in it's doing knowledge inferencing on facts. Okay, then again it's text to SQL parser which are used which use knowledge graphs. And the most important one that people should definitely go through is this one. There are a lot of papers that have come out recently for knowledge graphs. This is one of the papers that I found very interesting. This was in ACL 2020, and it talked about how we can transform relations with graph context modeling. So it might be a bit complex initially, but you will get an idea of what knowledge embedding, what knowledge graph embeddings are, how we are getting context in text when we are building knowledge graphs, how it's capturing the entities and relation and the entire graph structure into embeddings, and how it is helping us in building better and better NLP applications. So when even as humans, like when we store information as humans, we store it. Many people have argued that humans store information as knowledge graphs. Okay, so it's like everything is related to something. So for example, you will see there are certain memories that are very related to some event that has happened. Okay, say a particular song that was going on in the background when some event was happening. Okay, so when you hear that song, you might remember that event. So this is basically a knowledge graph structure, right? So that is why people are focusing on knowledge graphs, because because the aim of AI is to build systems that are close to human intelligence, right? So the way people think, the way people store information, if we are close to that, then obviously we'll slowly move into something called AGI, or artificial general intelligence, which is sort of doing things exactly as humans do, which is strong AI, or AGI, which is a broader term these days. So now we'll go into the implementation part. Okay. Let's see if my Colab is connected. Just give me a couple of minutes for the so I'll share this this Jupyter notebook with you guys.
Yeah, in the chat box.
No, I'll download it and share it. I'll share the file. I'll share both the presentation and then this file I'll share.
Okay.
So in order to share this Colab notebook, I have to share it with individual sort of email IDs. Okay. It's better to share the
right.
Jupyter notebooks. So what will we be doing as part of this implementation is we'll be first doing information extraction. First, we'll see how we can extract meaningful information from unstructured text. Then we'll be seeing how to construct knowledge graphs from that extracted information. We'll do this for a very simple example. We will take some. I've taken some sentences on India. Okay, I've skipped Lionel Messi for this part because I was afraid people would think I was obsessed with him. It's nothing like that. I'm a fan definitely, but okay. So India gives it a patriotic feel. So I've kept some sentences on India, and we'll try to see how we can extract useful information from these sentences, and we'll build a knowledge graph. Can we also visualize that? That is the first part, just to understand the process. Once we do that, we'll run the same set of steps on unstructured Wikipedia data that I've cleaned and kept. Okay, I've not put the pre-processing and textual segmentation part here because they are very basic and they are NLP specific thing. They have nothing to do with knowledge graphs anymore. So now that we have our notebook ready, so these are the libraries that I've imported. Some generic libraries are there. Pandas I've used to store the data frames for the extracted information that we get. Some NLP specific libraries, obviously Spacey will be there. And this is the Spacey model called EN Core Web SM, which is the English specific model for Spacey. And we have matcher for matching the different regular expressions or whatever sort of matching we want to do for the dependency graph, dependency labels that we extract, right? And this is for displaying the knowledge graph, network X and matplotlib. Quickly run this. Give me just a moment. Change the okay, so we'll see the first let us go through the dependency parser. So anyone wants to write a sentence in the chat that we want to see what sort of label comes up. I'll start with one. So again, John and the same sentence that was okay. So what it will do is, so in case of Spacey, what you have to do is, there's an API called NLP. You have to just pass the text into that, and then it will return an object, and you can iterate over that object. So it will basically contain words. It's an iterator basically. Okay? And you can the token dot text. So if you iterate over it, every iterated like object in the token. Yeah, sorry.
Yeah, please go ahead.
This is the textual part, and this is the dependency label. So as you can see, it has identified ball as the object and John as the subject. Okay, AUX means auxiliary to the root, which is hit, and the is a determinant. And so it determines the object. So this is dependent on ball is dependent. The is dependent on ball. Any suggestions so far? So we can give a bigger sentence if you want. So we can put that same sentence which was asked. Let's okay. So compound is, it's sort of adding more meaning. So the object would be Real Madrid here. Again, Juventus is another object. So you have multiple objects it has identified. And who is the subject? Cristiano Ronaldo. And played as the root. So you see how powerful dependency parser is. So it is able to identify multiple subjects, multiple objects in a particular sentence. Okay, so that is why we are using dependency parser to extract our required nodes and edges for the knowledge graph. Okay, moving on. So we have taken a set of sentences on India so that we can form a knowledge graph around India. India is known as Bharat. India is a country in South Asia. India is the 7th largest country. So on and so forth. Around 6 sentences we have taken Ramnath Kovind and Narendra Modi. Okay, so let's quickly go over this. We have taken this list of sentences. The second sentence would be India is a country in South Asia. That is correct. We put this in a data frame and we name the single column obviously as India. Let's see how it looks. Okay, so all the sentences have come here. We put it in data frame. Now to extract entities, now comes the information extraction part. So you know already what we'll be using for information extraction. We'll be using the dependency parser, right? We'll be using the dependency parser to find the subject and the objects, okay, and also the relations. So relation would be the predicate in this case. So we'll be using something called matcher in Spacey to do that. Okay, so to get entities, we first define a head entity and a candidate entity. So we are doing text segmentation for sentences here, and we have built a very basic. I've done a very basic implementation of this just for you to understand how basic knowledge graph construction for NLP works. So I've taken two variables called previous token depth, which basically is the dependency tag of the previous token, and previous token text, which is the previous token actually means the word here. Okay. So what we are doing here, we are iterating over each word in the sentence. So we have taken the sentences input, and we are passing this into the NLP API of Spacey, and we are iterating over this. So token dot depth underscore would give me the dependency label. So what is the dependency label? These are the dependency labels: n sub j, root, prep, compound. Okay, so the ones that we need to remember are, so for example, if I say Ronaldo. Let us do something with Ronaldo. So you see there is no object. It has not identified any object here. Okay. So because the sentence is ideally not a correct sentence. Okay. It should be Ronaldo plays football. What it has done is it has extracted player as an attribute. So if we sometimes consider wrong sentence structures also, we can extract the attribute here and the compound. Okay, there are some let us say. Okay, so a mod is a modifier. So what it is it modifying? It is modifying football player. So good football player or football player. You can extract all of these three. You can extract just the two. If you don't want to extract the modifier, that is also fine. You are trying to build knowledge from here, right? You are trying to find the main entities here, the subject and the object, and then the predicate would be is here in this case. Okay, so there are three dependency labels that I want you to notice here. First is a mod, which is a modifier, compound football, which is a compound, and player, which is an attribute. Okay, so we'll be making use of all of these three to extract our entities. And then we have n subject, and we have already seen how object comes. It's obj, right? Which ends with obj. Different types of object, dobj, pobj, different types of dependency tags are there. But they are all some sort of object. We don't need to understand what type of object they are. So first, what do we do is we check if it is not a punctuation. Just for a check, we have cleaned all the text. We'll always clean the text. But still, if in some cases we need a punctuation, so we just need to check if it is a punctuation. If it is not a punctuation, we'll see if it is a compound or if it ends with mod, because it can be different type of modifier. In this case, if it is an adjective modifier. Okay, so if it ends with mod or if it is an attribute. If it is any of these, we'll add it to something. We'll add it to something called prefix, which we have defined as a non-string here. So prefix becomes the text. So in this case, first one we have encountered is good, right? So prefix will go into good will go into prefix. Okay, so currently prefix contains good. Now we'll see if the previous token was either a compound or a modifier or an attribute. I've added all of these in the comments for you to understand better. Okay, so what do we do is we add it to the prefix. So for example, when I go from good to football, I know the previous token was a modifier. The current token is a compound. So if it is a compound and the previous token is a modifier, so what we'll do is it will add good and football together. Okay, so we can keep doing this in a loop. So it will capture all of this good football player and all of this, but we don't actually need it. We need to capture the last part of the compound or more modifier or attribute. We can keep adding all of that, but it's not necessary. It will increase the overhead unnecessarily. So once we have captured the prefix, we have captured the descriptors of the subject. What we do is we search for the subject and we add it to the subject. So head entity is our subject, right? So head entity we add it to. So in this case, our head entity would become just Ronaldo in this case. So if I say Cristiano Ronaldo here, so Cristiano is a compound. So Cristiano Ronaldo will become my subject. Okay. So I'll show you how I'll take this same sentence. I'll show you how it works. Okay. So same thing for object. In some cases, the object does not come, subject will always come. A sentence without a subject is not a correct sentence, right? So the example that I showed you, right? Ronaldo is a good football player. In this, the object does not come. So in this case, what will happen is whatever the prefix is, it will treat that as the object. Okay. Okay, so let us run this. So it will again, it will keep the this part. So it will again relationalize the previous token, the text of the previous token dependency label, and prefix it will initialize to null. Why? Because subject we have already found. Now we need to find the object. So again, if prefix, there is something in prefix, it will keep adding it to that. So that is not something we desire. So whenever it finds a subject, it will clear all the strings. Okay. Then we start searching for the object. So once we find the object, again the same thing, we add the prefix to the object. So token.text will contain the text part of the object. Object here, what we are testing is the dependency label. Okay. So in some cases, candidate entry is an attribute. That is why we have kept this part. Candidate entity is equal to prefix, just as the example that we saw. So we update the variables because we need to keep track of the previous token and the previous text, because that we have to update at the end of the normal programming concept. And we return the head entry and the candidate entry. Okay. So let us test with the same sentence here. What to run this code? Okay, so you can see it has extracted Cristiano Ronaldo, and what is Cristiano Ronaldo is a footballer. Right, good part is not captured because we are capturing only one before. Yes, right. It's updating it. Last two it will capture. So it is captured football. We can go for good football player also. So in that case, you have to just put this in a loop till you are getting compound or attribute. We keep adding it to prefix, nothing else. Just add a loop here instead of just two items. Just add a loop. Okay. So this part I think is clear. Any questions at this point? Okay. So we have extracted all the sentences in a data frame called India_df. Now what we do is we run this get.
Abhishek, you could unmute and say. He says that how literals be treated.
Can you please explain your question?
Abhishek?
Yes, sir. Sir, is there if there is any literal value in the sentence, how it will be treated?
Literal value as in number.
Like like Messi scored 3 goals against Brazil or something like that.
Okay, fine. So let us put this in. This is what you mean?
Yes, sir.
Okay.
And if we add a country also along with it, so
No, so this use case is basically for one subject, one object, right?
Okay, sir.
Yeah. So for the other use case, we have to build a much more complex system. So this is what you are talking about, like literals, it will be able to capture. Dependency parser is there, so we'll be able to do all of that, but this code will be much more complex. So it's very difficult to explain more complex code in such short time. Okay, so now what we'll do is we'll extract the entities from the data frame that we created. Let us list the entities that it has extracted: India, Bharat, India, South Asia, India, largest country, India, democratic country, India, Ramnath Kovind. And if you want to see the last one as well, India, Narendra Modi. Okay, so it has extracted whatever entities we had, whatever we wanted it to extract, it has extracted. Okay, now extracting the relations, this is very simple, but for this, some prior knowledge of Spacy would be better. There is an API called Matcher. So nlp.vocab, what it will do is it will take the vocabulary of English, okay, vocabulary of the set of sentences that we have given it, Okay, and then what it will do is it will take the root and it will take any sort of dependence like a preposition or an agent or an adjective around the root. So as place for, right? So for would be a sort of operative around the root, nothing else. So we are extracting the root. So the same sentence, if you see, the root is here. We don't need anything around it. Okay. So if I say Cristiano Ronaldo plays for Juventus. Okay. So prep, you can see this. So there was a question I think Apurva was asking, right? That how can it extract multi-word predicates? So that is how we are extracting multi-word predicates. We are taking the preposition as well as the root, combining both of them. So there can be different cases. There can be agent, there can be an adjective there. Okay. So we are taking just the dependency, that when the dependency label is either, when it is the root, it will definitely capture, or if it is a preposition around the root, an agent around the root, or if it is an adjective of the root. Okay, in that case, we'll be capturing those sort of patterns. Fine. It will match the dependency labels against this pattern and it will select from it. It is very simple. So whatever matches we have, we'll take the last two matches we'll be taking. So we'll not be taking all. Just like in the case of entities, we'll be taking 2-word predicates normally will be captured. We can take more. Just for simplicity, I've kept it as 2 words. So let us run this. This is very basic. This is sort of regular expression matching. Just it is matching the dependency labels and around the root, and then it's capturing it. Any of these, it will capture that. Nothing else along with the root. Okay, so let's run this code, and we will be running this on India DF. Okay, I've put. If you guys don't know what TQDM is, this. This part which it is showing is what TQDM. We showing the loading part which happens in apps. So let us see what relations it has extracted. India is known as, so first one is known as. So it has extracted multi-word predicates also. Okay, so now we have extracted the entities like the subject, object, and predicate. These three things we have extracted. Now what we'll be doing is we'll be separating. So in entity pairs, if you see, entity pairs is a list of head entity and candidate entity, or subject object pairs. Right? Now we'll be separating the subject and the object. The subject or the source node, object or the target node. So the 0 index of entity pairs is the subject, and the 1 index of the entity pair is the object. Okay, so we extract the source from there and target from there. If you want, I'll just show you what is captured inside source. You can see the first, all of them are India. So the source node for all of the questions, all of the sentences that we had is India. And if you want to see target, it is the second part of the entities, like Bharat, South Asia. So this is what we're extracting. We have just separated the subject and the object. Okay. Okay, so now what we do is we create a data frame in the structure that the subject will be first, then the object, then the predicate. Basically, source node, target node, edge. We are now starting to form the. Now we are starting to prepare to construct the knowledge graph. We have extracted the information that we needed. Now we have started with the knowledge graph construction. We are preparing the information in such a way that it can be ingested into the knowledge graph. Okay. So we define a DF called KGDF, and what we do is we add the source, target, and edge as source, target, and the relations we add. So relations we have already extracted, right? This is the, so we add it to this DF, and you can see there are 3 columns: source, target, and edge. I don't think there should be any confusion at this point, but still, after this we'll go into knowledge graph construction. There is nothing to understand there, just code. So if you can, conceptually, it's still this point that you need to understand the code. The rest all is just implementation. So any questions that you have at this point? Okay. Can we convert Neo4j KG in RDF graph? We have JSON file. I'm not really sure about that. I'm not really sure. So,
Sir, is there any reason? Hello?
yeah.
Sir, is there any reason to put the ages or the relations at the end, or it is normal thing?
No reason. Anyway, you
Okay.
can just showing just India, Bharat, edge, known as. So just you're putting it. You can put it in any way. Does not matter at all. Okay. So now that we have created the knowledge graph that can that we have already extracted the information for the knowledge graph, we'll construct the knowledge graph. So what do we use for it? We first create from network X, there is an API called from pandas edge list. So it will take the data frame from pandas and it will create the edge list from. Okay. So what it will be using is something called a multi-directional.
I want to interrupt because we have next 7 to 8 minutes. We are running short of time.
Yeah, sure.
Right.
We are almost done. So we pass as arguments the data frame that we created, the source, the target, and the edges. Okay. So for using this in the multigraph, you normally edges are kept at the rightmost, but I've seen some implementation where they keep edge before also. Okay, it does not matter. So you have to mention in that case, nothing else. Okay, so source to target will be creating an edge list here, nothing else. Okay, so it will not show the edges, what is the relation between them. It will just show the edges. So why we need the edges, I'll come to that in a bit. Actually, for this graph, we don't need the edge column at all. So edge attribute will keep as true, and we'll be using a multi-directional. So this is part of the network X library in Python. So like not a lot of to understand here. Let's create the network X object here, and now we'll be using matplotlib to plot it. So this is just basic. We'll be using the KG India network X object that we created. We'll be using Spring layout here. And we will be using the network X Spring layout object to set here. So these are the positions where it needs to plot. Okay, and we'll be using network X.draw. So the node colors we have mentioned as light green, node size we have mentioned as 1500. These are all parameters. With labels we have put as true. Otherwise, if we put as false, it will not give the labels. Difficult to understand. And then we'll be plotting it. So let's quickly plot it and see. So this is the knowledge graph that is created. So you can see for every from unstructured data that we have taken initially, this is just a simple application for it. So it has created the edges across the entities, the subject and the objects that we extracted. India, Narendra Modi, India. Right. This is a simple example. So now let us take a large unstructured data. So I have already created and kept something using because pre-processing, first of all, pre-processing and text segmentation will take a lot of time on such big data. Okay, and I clean it because it's not a session on NLP, right? It's on knowledge graph. So I have cleaned the data and kept it. So this is the dimension. We have 4,318 sentences. So let us see some sentences from there. Okay. These are just random sentences, which are there. Okay. There will be some similarities which will be coming out in the knowledge graphs. That is why we are creating the knowledge graphs, to understand some patterns, some relationships which are there in unstructured. This is completely random. So let us have a look at how these sentences look. So I can put around, say, around 20 sentences here. Okay. The temple is set on fire. Christian is then paralyzed by an elder, but she injures Quicksilver. So you can see it's just random sentences which are completely random sentences, completely unstructured text. Okay. So now we'll be creating knowledge graph using the same exact functions that we have used so far. So first we create the entity pairs. It will take some time. I'll show you some entity pairs. I'll create the relations. I'll look at if anyone has any questions.
Sir, in the previous knowledge graph that you have shown,
yeah,
there is no predicate. It is not mentioned in the graph actually. So
yeah, it's not mentioned. So you can do that. It's just I didn't show that because in some cases there are so many edges. If we put text on those edges, you can't understand anything. I'll show you one sample. From this data it will be much clearer. So I'll not run the code then for it. I've actually, so from this data set that we have created, that we have taken, this unstructured text, this is the knowledge graph that we get. So now try to identify one edge. So you can't even identify the nodes, how to identify the edges, right? So this is how it will look finally. There are so many nodes and so many edges. Okay, so relations we have done. Source and target will separate. We'll create the data frame from that. Let us have a look at some cases. Okay, same thing that we have done before. This is just on unstructured text. So I'll show you some relations that we have extracted, which are the maximum relations or the edges that we have extracted for the knowledge graph, right? The maximum is, then we have was, released on, composed by, then we have introduced in, we have produced in 9 times. Let us take something which has come directed by, is there 16 times, composed by 35 times. So we can sort of make some sense from this, right? If you take the entire, construct the knowledge graph on the entire data set, nothing is visible. Obviously, this is just for visualization. When we use it for an NLP application, we are just querying that knowledge graph, we are traversing that knowledge graph. In that case, it's just for visualization. Let us take one particular relation. Okay, so I'll take, say, composed by or directed by, written by is also there. And take composed by. So composed by is already there. Let's take, okay, composed by, directed by. So what we did here is we have taken the edges. This is why we need the edge column. In the previous cases, we didn't require it because we are not putting the text there. Here we are using only one type of relation. So we don't need the relation to be printed out in the form of text. And actually this for knowledge graph visualization, the text is normally not printed there. So we have taken the directed by relation only, same code, all of the things, remaining things are same. Let's run this. Okay, so this is the directed by knowledge graph that comes. If I use composed by, there are more edges that will come here. These are the edges. You can see music given by Preetham, by Brian. Okay, so A.R. Rahman is there. A.R. Rahman is in the soundtrack score. So it's a reasonably good knowledge graph that we have extracted. Okay. So that is sort of all that I had from my end. I'll go back. I will be sharing everything from my side. So these are the references that I've taken for this presentation, for this talk. Any further questions, comments, if you have, go ahead and ask. So we have like 5 minutes, ma'am.
Yes, please.
Okay. If you want me to go back to the code also, that is fine.
Yeah, if the participants wish, you could ask questions. Otherwise, I could see it was otherwise also interactive on the way.
Yeah.
So later on also, if you have any queries related to it, because I'll drop down all the related material in your shared folder. So if you have any queries further, you could drop to me. I could pass on to the expert. There is one Wikipedia category graph. Do they help to create the knowledge graphs?
I am honestly not aware of this. So I am not a knowledge graph expert per se. I know some applications
that is true.
Graph in NLP. I'm an NLP expert, honestly.
This is for this particular workshop. It was like I was after you that yes, please come up with something for knowledge graphs for hands-on or a demonstration session. So it was really, really wonderful and beautiful what you did in such a small time.
Yeah, thanks.
So Arindam, I could see you have already answered most of the queries.
Yes. If
all
anyone
of the queries by now.
Since Ravindra Kumar Pradhan says how to implement KG in neural networks. I didn't get your question.
Actually, what he's asking is how to do the hybrid. Means for utilizing the knowledge networks, how could we utilize the knowledge graph? Maybe as background knowledge or.
So I shared one paper, right? Just a moment. Not this one. Yeah, this is one paper. So over here you can see that how knowledge graphs are being used to create something called knowledge graph embedding. All of this are done using neural networks and deep neural networks. So knowledge graph embeddings definitely have to use neural networks. So directly how to create knowledge graphs using neural networks, there are a lot of papers on that. So I don't recall right now. I can tell you about how knowledge graphs are used for natural language processing, because NLP is my domain. Knowledge graph would not be, I would not tell knowledge graph is my domain.
So thanks, Arindam. I hope we could terminate and close the session now. Sure. This particular session for the time being.
Okay, thanks a lot, guys. Thanks, ma'am, for this opportunity. I hope I could help you and sort of provide some sort of information to you guys. Okay. Thanks a lot.
Yeah, definitely it was a great session, and I'll try to connect with you back for the 21 to 25, the second workshop in the series, the same month.
Yeah, right.
So I'll talk to you regarding that. Okay, thank you so much. Thank you. Bye-bye. So guys, let us join back tomorrow morning, 9:30 sharp, with Sumit Bhatia with us. And
Ma'am,
he'll also be talking on knowledge graphs.
Ma'am,
Pardon?
it will be better if you get the mail ID for communication.
I'll pass on to you. I'll pass
Okay,
on.
ma'am.
Arindam, will you like to share your email ID? I think he is left. Okay. Oh, hold on. Let me do it right now so that it will be better if I do it right now. Okay, Apurva. Okay, I'll share it later on. No problem. Whenever you
Okay, ma'am.
wish, you could connect. I'll share. Okay, then see you guys tomorrow morning 9:30, and then just an announcement at sharp 2:45 tomorrow. After the 2 sessions in the morning, we'll have a lunch break. Then sharp 2:45 will be starting the test. 50 minutes test will be there, and then we'll be moving for the valedictory function. Some delegates, directors of the institute will be joining us in the valedictory session, possibly 30 to 40 minutes just, and by 4:45 sharp we'll be ending everything tomorrow. And I really hope that this FDP will be a turning point in your research. So bye-bye for now. Have a good day.